Okay, in this video, I'll go through a portion of kinetics, and specifically, I'm going to go over Newton's laws of motion. So kinetics is the study of forces causing motion. That's a branch of mechanics. In this class, we really talk about kinetics in the linear world and in the angular world. Linear is motion where all points of an object travel the same distance. Not necessarily a straight line. We can be on a curved path. But in essence, we look at linear kinetics in an X, a Y, and a Z dimension or direction. And then angular kinetics are kinetics or forces that tend to cause rotation. And so we start using terms like torque and moment. In this presentation, I'm really just going to talk about kinetics from a broad, big picture perspective. So really, I'll be using more linear kinetic phrasing. You need to know Newton's laws of motion. In this class, and really in our department, we really focus on what we call a Newtonian approach to understanding the physics of some movement issue. And it's Newtonian approach because we use Newton's laws of motion. There are other approaches to physics. But this is one that is fairly straightforward and works. But you'll find that there are some twists in understanding Newton's laws of motion, even though the three laws are very easy to memorize. So first, you want to memorize these three laws of motion. And then second, we're going to learn how to apply these three laws of motion to understand performance. So the first law of uniform motion, also known as law of inertia. Inertia is quantified by the mass of an object, and inertia represents an object's resistance to change motion. An object with a lot of inertia has a lot of resistance to change motion. An object with very little inertia it's very easy to change its motion. So I always like to use a bowling ball versus a ping pong ball. A bowling ball has lots of inertia. It's hard to get going, but it's also hard to stop when it's moving. A ping pong ball has very little inertia, very easy to change its motion. It doesn't take a lot. It's easy to get it going as well as easy to stop it from moving. All right. So this first law is law of uniform motion or law of inertia. You see it. And it's written as every object continues in its state of rest or uniform motion in a straight line unless a force changes the motion. In essence, this is an observation. What this is simply saying is, if I take this cup and I put it here, this coffee mug, this coffee mug is going to sit in this position until something comes along and changes its motion. Right now it has no motion. But if I push on it and I give it some motion, now I've changed its motion. We can think of motion in this context as the velocity or rate of change of displacement of the object. All right. So if an object is at rest, it's going to continue to stay at rest until a force comes along and changes that object from being at rest and gets it moving, gives it some velocity. The other trick with this law is when an object is moving, it will continue with that state of motion until a force causes that object to change its motion. You know, this is an easy example. If you take an object and you slide it on a surface, well, what's going to happen? Well, if it's sliding on a surface, I think we all know eventually we'll come to a stop. All right. But if we make that surface super, super, super slippery, ice, for example, or really, really super smooth surface, and we give an object a little push and it starts moving, it's going to continue with that velocity until something causes that velocity to change. And that something is a force. So it's going to continue with a state of velocity. It's going to continue with constant velocity until something causes that object to stop. Now, as I said in the beginning, I said if you push an object on a surface, it's eventually going to stop. Well, why is that? Well, because there is pushing on the object, and we know that as friction force pushing on the object, friction force. It's a force that's causing that object to change its motion, change its velocity. All right? And we'll get into friction later on in the semester. But for the purposes of the first law, an object will stay at rest or stay with constant velocity until a force comes along and changes that velocity, either from 0 to something or from something to something else, either an increase in velocity or a decrease in velocity. All right, so the first law of motion, first Newton's law, is an observation. It's an observation of how things behave. The second law is a definition, law of acceleration. It's a definition of what a force is. In this case, I've got some words here. The rate of change of motion, the rate of change of velocity, which we know is acceleration of an object, is proportional to the force applied on the object and in the direction of the line of application of the force. What does this tell us? Well, it's proportional, meaning the harder I push on that object, the more the acceleration is going to be of that object, the more the rate of change of velocity there will be. And it's in the direction that you're pushing on the object. Okay. Now, what's important, the equation, and I don't have it listed here, the equation that defines this law is F equals ma. The F equals mass times acceleration. If we wanted to represent this law, we would actually have F, and then we would use a proportional sign and then put A on the other side of that proportional sign, where we say F is proportional to acceleration or acceleration is proportional to F. Either way. It's equal, the equation, we put an equality sign in there when we put M in the equation, mass of the object. Mass represents the object's inertia. If we know the object's inertia and we know the forces acting on the object, we can then figure out the acceleration of the object. Okay, so Newton's second law is really a definition of what a force is. F equals ma. Force causes acceleration. All right, and the trick with this second law is the word in quotes there, on. We need to know the forces acting on the object, and then we can understand the acceleration of the object. So these two laws were really well known, even when Newton put together his three laws of motion. And he recognized that. I mean, he's the one who said, stand on the shoulders of giants and doing things. Anyways, the third law is really his contribution to these three laws of motion. And that's law of action reaction. Easy one to remember. Most of you already know this. For every force applied on an object, there is an equal and opposite force applied by the object. Or you could say this, for every force created by an object, there is an equal and opposite reaction force. Either way, okay? But forces come in pairs. If I push on an object, the object pushes back on me. If I push on this coffee mug, the coffee mug is going to push back on me. If I push on the ground is going to push back on me. For every force, there's an equal and opposite force. The important part of these three laws is that when we use Newton's second law, we only identify the forces acting on the object, not by the object. And then we put those forces into an equation, and then we understand the acceleration of the object when we know the mass of the object that is being accelerated. So this is where things get a little tricky. And sometimes we do what I call mental gymnastics, where I often want to know the forces that I am creating or a person is creating. I can't actually measure the force of the muscle, but what I can do is measure the reaction to that force. I can measure the force of the ground pushing on the person. I can measure a pushing on put a sensor on a device. I can measure how much pushing there is on the object, and then I can get the reaction force. So that is something we take advantage of in biomechanics, is that we know forces come in pairs. All right, so let me go through this a little bit more. I'm already going through what I'm already saying. Okay, so this is just some additional slides teasing out each law. Law of uniform motion, Newton's first law, an object at rest will always stay at rest. An object moving will continue to move unless a force is applied to that object. And that force will cause a change in motion, which is a change in velocity. This law states that velocity will be constant, acceleration is 0 meters per second squared, as long as there are no forces acting on the object. And really, the key here is no net force, because we can still have forces acting on the object, but they add up to 0 And then velocity would be constant, acceleration would be zero. So really, we're looking at a net force or total force. And this was a video at one point of an object rolling, but now it's just a static image. And the whole idea here is that this ball will sit there until something comes along and pushes on this ball, this billiard ball, and then they will move with some velocity. So just a quick illustration. All right, law of acceleration. When a force acts on an object, and again, I'm emphasizing the on part, it will cause acceleration. And we need to know all the forces acting on the object. And then if we know the object's mass, the inertia of the object, we can figure out acceleration or rate of change of velocity. So force units are newtons or kilogram meters per second squared. Mass of an object units are kilograms. And so you can do a unit analysis here too. Kilogram meters per second squared for acceleration. And 1 kilogram accelerated 1 meter per second squared is a force of 1 Newton. All right, so now I'll go through some examples. If we want to understand how this ball is moving through the air, why the kinematics of a ball follow the trajectory of the ball, why the ball does follow a certain path. All we need to know are the forces acting on the ball. And in this case, there's gravity and there's air resistance. And we'll discover air resistance more in subsequent lectures, but air resistance is a force, and it's a force of the air pushing on the ball. And what we know is that if we can throw this ball in a way that the ball spins in a particular way, we can actually create air resistance on more air resistance force on one side of the ball versus the other side of the ball. And that's how we ultimately get a ball to curve, right? Because the forces acting on the object will cause that object to accelerate in a particular direction. And we'll go through this a little bit more when we do projectiles. And gravity is a force acting on the object, causing the object to accelerate in the vertical dimension, but not in the horizontal dimension. So gravity doesn't really explain why a ball curves. When you really need to understand air resistance force to understand why a ball curves. What forces are acting, on Michael Jordan while he's going through the air here to score some points? Well, again, gravity and air resistance. If we can identify these forces acting on the object, we can understand his acceleration. I should actually emphasize that the acceleration that I'm talking about is the center of mass. So obviously, as he's going through the air, his arms are moving, his legs are moving in particular ways. But if we look at this acceleration of the center of mass, it's perfectly predictable by knowing the forces acting on the object, in this case, on Michael Jordan. And when he's airborne, the only forces acting on him are gravity and air resistance. So his motion is determined by these two forces. Likewise, when we're looking at running, and we'll go through more examples throughout the semester, but as we look at running, we identify forces pushing or pulling on the object. In this case, we still have gravity, which we're almost always going to have gravity as a force for the types of movements that we're looking at. And we have the ground reaction force, or the force of the ground pushing on the runner. And we also have a little bit of air resistance. If we know these three forces, if these are all the forces acting on the person, we can understand that person's kinematics, the acceleration. Now notice I'm only talking about forces acting on the person, not forces created by the person. But I often want to know the forces created by the person. Well, what we'll learn as we go along, this ground reaction force is in reaction to what the person's doing. And so this is where I do those mental gymnastics, that if I want to know the forces that the person's creating, I actually measure the reaction force. And then I can understand the forces the person is creating. But to use Newton's second law, I only need to identify the forces acting on the object. And so we start doing what we call free body diagrams, or we start drawing arrows on objects, where sometimes we actually just draw the center of mass of an object and then draw all the forces that are acting on that center of mass. But in this case, I've just added a whole bunch of arrows, and these are all forces. And what we need to do is figure out our perspective of what object we're interested in understanding. So here I put forces acting on the rider and I bolded that, okay? Because I'm interested in this example, what pushing or pulling on the rider there is. In this case, I've got a force pushing here, one pushing at the elbows. I've got air resistance pushing. I've got gravity pulling down. I've got the seat pushing on the person, and each pedal is pushing on the person. Those are all the forces acting on the person. Now, if I was interested in the bike rider system, then it's a little different. Notice I did not put an arrow here on the bike because the question I put here, or the task I put here, was forces acting on the rider. And so what we really need to pay attention to when we start doing our kinetic analysis is the object of interest. And once we know the object of interest, then we need to identify forces acting on the object, and then we can understand forces created by the object. All right, but in this case, I did not include forces pushing on the wheels, which we will do later on in a different lecture. I only identified forces acting on the rider. And then we add up all those forces, we're going to understand the cyclist's center of mass, acceleration of the center of mass. And here's just another example illustrating that same point. Here's weightlifting or some type of deadlift here. What forces are acting on the lifter, on the person? Well, gravity is still pulling down on the person. Well, now we've got a force at each hand, and we also have forces on the ground, pushing on the person, pulling on the person, pulling on the person. All these are forces acting on the person. This is not forces created by the person, although we know from Newton's third law, there's an action reaction. For every force created by the person, there's an equal and opposite force. So here, this is the force acting on the person. Equal and opposite is what the person's doing. To use Newton's second law, we identify forces acting on the object, not by the object. So again, Newton's third law is going to force us to do a little bit of mental gymnastics. And so now here, if we go the other way, what forces are acting on the weight? Well, now I've got gravity pulling down on the weights. I could have drawn that as one arrow, but I did it as two. And I also have the person pulling on the bar. Okay, the hands pulling on the bar. So now if I know all those forces, I can understand the forces of the acceleration of the bar, of the weight itself. So this word's going to become really important when we're doing a kinetic analysis. When we're looking at forces causing movement, we really need to understand what forces are acting on that object. And once we do that, we can understand, we can put those forces into that equation, F equals ma, and we'll understand the acceleration of the center of mass of the object. All right, so Newton's second law, identify all forces acting on the system. Push or pull that tends to cause motion, that's a force. Use the equation sigma, sum of forces acting on the object, cause that object to accelerate. And I really should put COM right here for center of mass of acceleration. Now, often what we will do, and we do this in research, we do this in class as well, is we analyze forces in one dimension at a time. So we'll look only at the forces acting in the vertical direction. Then we understand the acceleration of the center mass in the vertical direction. Or we may look at the horizontal direction. We understand the acceleration in the horizontal direction or medial lateral, for example. And this reverts back to Newton's first law of motion. When a force acts on an object, it will cause acceleration in that line of pull or push of the object. And I've said this, but there's just some text here. You can understand forces caused by the object by understanding the reaction forces. So this is just something that we do quite a bit in our research, and you'll see this in the readings as well. Okay, so know Newton's three laws of motion. To use Newton's second law, you need to understand the forces acting on the object, not by the object. We will do free body diagrams, and in those free body diagrams, you only are identifying forces acting on the object, not by the object. In order to understand the forces created by the object, we often measure reaction forces acting on the person. And remember, forces cause kinematics. Forces cause acceleration. Accelerations don't cause forces. All right, so just a little bit of semantics. Okay, that's it for Newton's laws. Thank you.